Everyone knows light. It's the universe's ultimate speed demon. From Earth to the Moon in a blink, across our entire solar system in mere hours. It feels impossibly fast, right? An unbreakable record. But what if that absolute truth was actually the most terrifying lie? The chilling reality scientists rarely dare speak aloud. Light is excruciatingly, hopelessly slow. So slow, in fact, that it transforms the cosmos into an inescapable prison, with us locked firmly inside. Prepare to have your understanding of space, time, and humanity's place in it shattered forever. Look up tonight. Every photon entering your eye has been traveling for years, sometimes thousands, just to reach you. That light left its source long before you were born. Yet, it arrives, creating an illusion of an eternal, unbroken present. This is the universe's first trick. Light moves so fast its journey becomes invisible. We see the destination, never the travel. Light streaks through a vacuum at roughly 300,000 kilometers per second. On human scales, this speed is staggering. A beam fired across Earth would lap the planet 7.5 times in a single second. In the time it takes your brain to register a hot stove, light has gone from New York to Los Angeles and back roughly 10 times. Consider the Moon. 384,000 kilometers away. Light crosses that gap in 1.3 seconds. Apollo astronauts had barely noticeable delays. The Moon feels close. Light makes it feel even closer. This comfortable proximity is exactly what makes the truth so hard to accept. Now, the Sun. 150 million kilometers away. Light covers this distance in 8 minutes and 20 seconds. The sun you see in the sky is not the sun as it exists right now. It is the sun as it existed 8 minutes ago. If it vanished this instant, you'd see it shining for 8 more minutes. All of it, a ghost. This 8-minute delay barely registers, but it's the first whisper of a problem that will grow terrifying as we push further into space. Mars, at its closest, 55 million kilometers. Light reaches it in about 3 minutes. At its farthest, 22 minutes. NASA mission controllers already feel this. A rover encounters an obstacle. Minutes for the signal to reach Earth. Minutes for the command to return. The rover drives blind for half an hour. Even at light speed, Mars is far enough that real-time control becomes impossible. Push further. Jupiter needs 43 minutes. Neptune, over 4 hours. The Voyager 1 spacecraft, launched in 1977, is over 23 billion kilometers from Earth. A signal from it takes approximately 22 hours to reach us. Nearly a full day, for a message moving at the universe's fastest speed. And Voyager 1 has not even left the neighborhood. In nearly 5 decades, it has traversed less than 1/400th of a single light year. This is where the illusion cracks. A light year. It's the distance light travels in 1 year. Nearly 6 trillion miles. This represents the smallest meaningful unit between stars. The nearest star system, Alpha Centauri, is 4.24 light-years away. 40 trillion kilometers. Light, the fastest thing in the universe, needs 4 years and 3 months to cross that gap. A beam of light leaving Earth right now will not reach the nearest star until sometime in 2029. This is the closest star. The galactic equivalent of the house next door. Everything beyond it is incomprehensibly further. The speed that felt like magic, that made the moon feel close and the sun feel warm, now looks like something else entirely. Not a bridge. Not a highway. Something closer to a brutal reminder of just how vast and how indifferent the universe truly is. The distances were abstract. The numbers too large to feel real. It wasn't until we began measuring signal delays that the true scale of the problem started to sink in. A light year sounds like time. It isn't. It is distance. 9.46 trillion kilometers. 40 trillion kilometers to Alpha Centauri. To truly feel that number, if you could board Voyager 1, humanity's fastest long-distance spacecraft, and point it directly at the nearest star, you would arrive in approximately 75,000 years. 75,000 years. The entire recorded history of human civilization, from our first agricultural settlements to today, fits inside roughly 10,000 years. Voyager 1 would need to fly 7.5 times that entire span just to reach the closest star our Sun has. This is where we are. This is our cosmic prison. But what if we could go faster? What if future propulsion systems could dramatically exceed Voyager's velocity? Even at a seemingly incredible 1% of the speed of light, a blistering 3,000 km per second, 176 times faster than Voyager 1, the journey to Proxima Centauri would take approximately 425 years. That sounds like progress, but it's still an enormous span of time. When Columbus crossed the Atlantic in 1492, a 425-year mission launched that same year would still not have arrived at its destination today. The crew would have been dead for centuries. Their civilization might not even exist in recognizable form. 1% of light speed is simply not fast enough. Push to 5% of the speed of light, and the numbers begin to compress. Proxima Centauri drops to roughly 85 years. The nearest stars with potentially habitable planets fall to between 200 and 400 years. These are still multi-generational timescales, but for the very nearest targets, we're finally approaching something that overlaps with a long human lifetime. A crew member departing at age 20 might theoretically arrive at Proxima Centauri at age 105. Unlikely to survive, but at least the math fits within the outer boundary of biological possibility. The problem? 5% of light speed represents an almost incomprehensible engineering leap from where we currently stand. No propulsion system ever built or seriously tested comes close. At 10% of the speed of light, the nearest star becomes reachable within a single human lifetime. A mission launched when an astronaut is 25 arrives when they are 67. Brutal, isolating, and dependent on technologies we haven't built, but theoretically survivable. 10% of light speed is the threshold many researchers identify as the minimum viable velocity for a crewed interstellar mission. But look beyond Proxima Centauri, and the trap reasserts itself immediately. A star 20 light-years away takes 200 years at that speed. The TRAPPIST-1 system, with its 7 Earth-sized planets, takes 400 years. Any destination beyond about 15 light-years requires multi-generational timescales, even at 10% of light speed. And 10% of light speed is 30,000 km per second. In 2016, a project called Breakthrough Starshot was announced, backed by Stephen Hawking and Yuri Milner, with $100 million in funding. Its goal was to accelerate a spacecraft to 20% of the speed of light, fast enough to reach Proxima Centauri in roughly 21 years. But the spacecraft in question was not a vessel. It was a gram-scale chip, roughly the mass of a paperclip, attached to a reflective sail. The plan called for a ground-based laser array producing 100 gigawatts of power to push the chip to relativistic speed in about 10 minutes. It would carry a tiny camera, basic sensors, and a minimal transmitter. It would screen through the Alpha Centauri system in a matter of hours, take a few photographs, and vanish into the interstellar void forever, with no ability to slow down, orbit, or return. By September 2025, the project had been placed on indefinite hold. Of the $100 million pledged, only about $4.5 million had actually been spent. The engineering challenges, the laser array, the sail material, the survival of the chip across decades of interstellar bombardment, proved too severe even for the most optimistic projections. And this is the detail that tightens the trap. Breakthrough Starshot was designed for a paperclip. Not a probe capable of extended scientific observation, not a vessel capable of carrying instruments, let alone humans. A paperclip. If reaching 20% of the speed of light with 1 gram of payload is this difficult, the implications for anything heavier are devastating. The relationship between mass and the energy required to accelerate it is not forgiving. It scales mercilessly. The galaxy does not care how ambitious your engineering roadmap is. The nearest interesting destination is still 25 trillion miles away. And every kilogram you want to send there carries the full weight of physics. To understand why interstellar travel is so brutally difficult, you have to stop thinking about space the way it appears in textbooks. In most diagrams of the solar system, planets are neat circles, evenly spaced, with the sun glowing warmly. Everything looks reachable. These diagrams are lies. Not intentional ones, but necessary ones. Because if you drew the solar system to accurate scale on a standard piece of paper, the planets would be invisible specks separated by vast stretches of blank white nothing. And even that accurate solar system, blank and empty as it would look, sits inside a bubble so small compared to the rest of the galaxy that it barely registers as a dot. The scale problem in astronomy is not just a matter of large numbers. It's a matter of the human brain being physically incapable of intuitively grasping what those numbers mean. Imagine shrinking the entire solar system, everything from the sun to the outermost edge of Neptune's orbit, down to the size of a coffee cup. On that scale, how far away would the nearest star be? Not across the room, not across the building. Across a football field. And how wide would the Milky Way be on that same scale? Roughly the distance from New York to Los Angeles. The solar system, which already feels impossibly vast when you think about Voyager 1 spending 5 decades crossing it, is a coffee cup sitting somewhere in the middle of a continent-spanning disk of stars. And the Andromeda Galaxy, our nearest major galactic neighbor, visible as a faint smear of light in the northern sky on a clear night, sits 2.5 million light-years away. A photon aimed at Andromeda right now will not arrive for 2.5 million years. As we discussed, a light-year is the distance light travels in one uninterrupted year of motion at 299,792 kilometers per second. That works out to approximately 9.46 trillion kilometers, or just under 6 trillion miles. When astronomers say the nearest star is 4.24 light-years away, they mean that the distance between our Sun and that star is 4.24 times that number, roughly 40 trillion kilometers. There is no way to make that figure feel real through sheer repetition of digits. But consider this, if you could somehow board Voyager 1 and point it directly at the nearest star, you would arrive in approximately 75,000 years. The nearest star system to our own is Alpha Centauri, a triple star system. Proxima Centauri is the closest of the three, sitting approximately 4.24 light-years from Earth. In 2016, astronomers confirmed Proxima Centauri b, a roughly Earth-mass planet orbiting within its habitable zone. The discovery was electrifying, a potentially rocky world, capable of supporting liquid water, right next door in cosmic terms. A radio message sent to Proxima Centauri today would arrive in 2029. A reply, if anyone were there, would reach us in 2033 at the earliest. A simple exchange, a hello and a response, would consume nearly a decade. And that is just communication. Physical travel is an entirely different problem. At 10% of the speed of light, a velocity humanity has never come close to achieving, the journey would take over 42 years one way. At 5%, 85 years. At 1%, 425 years. These figures are for the nearest star. The nearest one. Every other destination in the galaxy is further, often by orders of magnitude. And yet, Proxima Centauri is already so far away that a spacecraft launched today at the best speed any serious propulsion concept has ever proposed would not arrive within a single human lifetime, under most scenarios. Move outward from Proxima Centauri, and the numbers grow savage almost immediately. Barnard's star, the next nearest single star, lies roughly 5.96 light-years away. Ross 128, about 11 light-years away, hosts a planet that may be temperate. Teegarden star, roughly 12.5 light-years distant, hosts a world that scored near the top of the Earth's similarity index. A radio signal sent in 2026 would arrive there in 2038. A spacecraft traveling at 10% of the speed of light would take 125 years. 2 full human lifetimes, and Teegarden star is still, in galactic terms, practically in our backyard. The TRAPPIST-1 system, which made global headlines in 2017 for hosting 7 roughly Earth-sized planets, sits approximately 40 light-years from Earth. A spacecraft launched toward TRAPPIST-1 at 10% of the speed of light on the day Columbus first crossed the Atlantic would still be in transit right now, with decades of travel still remaining. The Milky Way galaxy spans at least 100,000 light-years across its visible disk. It contains an estimated 200 to 400 billion stars. The galactic center lies approximately 26,000 light-years from Earth. Meaning that light which left the center of our own galaxy when early humans were painting caves in Europe has still not reached us. It will arrive in roughly 24,000 more years. Among those hundreds of billions of stars, astronomers now believe that a significant fraction host planets. Statistical analysis suggests there could be billions of Earth-sized planets orbiting in habitable zones throughout the Milky Way. Worlds where temperatures might allow liquid water to pool. As of early 2026, astronomers have confirmed more than 6,000 exoplanets. Each new world is a reminder that the ingredients for life are not rare. Carbon chemistry is ubiquitous. Water is common. Energy sources are available on virtually every rocky world. The raw materials for life are everywhere. The problem was never whether suitable worlds exist. The problem is getting to them. Every spacecraft humanity has ever launched, from Apollo to Mars rovers, has been powered by one basic principle: fuel burns, gas expands, pushing the vehicle forward. Newton's third law in action. This technology is elegant, reliable, and for navigating the solar system, it works brilliantly. For interstellar travel, it is so inadequate that calling it insufficient feels like an understatement. It is the wrong tool for the job. The reason comes down to exhaust velocity. A rocket moves by throwing mass out the back. The faster that mass is ejected, the more efficiently the rocket converts fuel into speed. Chemical rockets eject exhaust at roughly 4 to 5 kilometers per second. To reach a final velocity significantly higher than your exhaust velocity, you need exponentially more fuel. This relationship is captured in the Tsiolkovsky rocket equation. What it means in practice is devastating. If your exhaust velocity is 5 kilometers per second and you want to reach 50 kilometers per second, a pathetic speed by interstellar standards, less than 0.02% of light speed, you need a mass ratio of roughly 22,000 to 1. For every kilogram of payload, you need 22,000 kilograms of fuel at launch. To reach even 1% of the speed of light using chemical rockets, the mass ratio becomes a number so large it has no physical meaning. You would need more fuel than exists in the observable universe to accelerate a single kilogram to 1% of light speed using chemical propulsion. This is not an exaggeration. It is straightforward arithmetic. This is why every serious proposal for interstellar propulsion abandons chemical energy entirely and looks to nuclear physics instead. Nuclear reactions release roughly 1,000,000 times more energy per kilogram of fuel than chemical reactions. Nuclear fusion, which releases even more energy, offers a path to exhaust velocities that could theoretically reach several percent of the speed of light. There is just one problem: no fusion engine capable of sustained, controlled thrust has ever been built. The entire field of fusion energy, despite 7 decades of research and tens of billions of dollars in investment, has not yet produced a commercially viable power plant on Earth, let alone a propulsion system capable of operating in deep space. Antimatter represents the theoretical upper limit of energy density. When a particle of matter meets its antiparticle, they annihilate completely, converting 100% of their combined mass into pure energy. A single kilogram of antimatter annihilating with a kilogram of normal matter would release enough energy to accelerate a small probe to a meaningful fraction of the speed of light. It sounds like the answer. It is not. The total amount of antimatter ever produced by all of humanity's particle accelerators combined is estimated at roughly 20 nanograms. Not 20 grams. 20 nanograms. 20 billionths of a gram. Producing even 1 gram of antimatter using current technology would cost on the order of tens of trillions of dollars and take millions of years of continuous accelerator operation. But there is a deeper problem with antimatter. It is not a source of energy, it is a storage medium, and a catastrophically inefficient one. Creating antimatter requires energy input. You cannot get more energy out of antimatter than you put into making it. Antimatter does not solve the energy problem of interstellar travel. It relocates it, and wraps it in an additional layer of inefficiency that makes the total energy budget even more punishing. Now consider the actual energy numbers. The kinetic energy of a 1,000 kilogram probe, roughly the mass of a small car, traveling at 10% of the speed of light is approximately 450 quadrillion joules. To put that in perspective, the total annual energy consumption of the United States is roughly 100 times that figure. The energy needed to accelerate a single small probe to 10% of light speed equals about 1/200th of America's entire yearly energy output. Scale up to a meaningful crewed vessel, something capable of supporting human life for decades, and you're looking at a spacecraft massing at least 100,000 kilograms. The energy requirement jumps accordingly, reaching figures that exceed the annual output of entire nations for a single mission. These are not theoretical curiosities. They are hard physical constraints. Energy cannot be created from nothing. And then there is the problem that doubles everything: deceleration. Every discussion of interstellar travel focuses on acceleration. But arriving at a destination requires stopping, or at least slowing down enough to enter orbit. Slowing down costs just as much energy as speeding up. If you accelerate a spacecraft to 10% of the speed of light, you must spend the same amount of energy again, applied in the opposite direction, to stop. For any mission architecture we can currently conceive, stopping is very nearly impossible. There is a temptation, when confronted with the energy wall, to assume that sufficiently advanced technology will eventually overcome it. And to be fair, history gives some reason for optimism. Humanity went from horse-drawn carts to jet aircraft in roughly 2 centuries. From the first powered flight to landing on the moon in 66 years, the pace of technological development has been extraordinary. But there is a category of problem that technology improves, and there is a category of problem that technology cannot dissolve because it is not an engineering limitation, but a physical one. The energy wall is the second kind. And even if we grant the most generous possible assumptions about future propulsion, a second wall immediately appears behind it. One that has nothing to do with engines or fuel, and everything to do with biology. Every organism we know of has a finite lifespan. Humans, even under the best medical conditions, rarely survive past 110 or 120 years. The average lifespan hovers around 80 years. A mission to Proxima Centauri at 10% of light speed takes about 42 years one way. Survivable, in principle, for a young and healthy crew. But a mission to a star 20 light-years away at the same speed takes 200 years. No human alive today, and no human who will be born under currently understood biology, can live that long. A mission to Teegarden star at 10% of light speed takes 125 years. To the TRAPPIST-1 system, 400 years. These are not exotic, far-flung destinations. These are the closest candidates we have already identified as potentially interesting. And every single one of them beyond the very nearest star exceeds the outer boundary of any human lifetime under any medical scenario currently imaginable. The standard response to this problem is to propose generation ships, vessels large enough to sustain a self-reproducing population across many generations. The crew that launches the mission is not the crew that arrives. Their descendants, born and raised entirely aboard the ship, complete the journey. This concept has been explored extensively in science fiction and has received serious academic analysis. On the surface, it sounds like a reasonable engineering solution to a biological constraint. In practice, the challenges are so monumental that most researchers who study the problem in detail conclude it may be fundamentally unachievable. A generation ship would need to be a fully self-sustaining ecosystem, recycling all air, water, and nutrients indefinitely for centuries, with no possibility of resupply or external repair. It would need to support a population large enough to maintain genetic diversity across that entire span. Geneticists estimate a minimum of several hundred to several thousand individuals. It would need energy sources capable of running for millennia without degradation. And it would need social structures robust enough to maintain mission coherence across dozens of generations. That last requirement may be the hardest of all. No human organization has ever maintained a coherent institutional mission for more than a few centuries without undergoing radical transformation. The idea that a ship-based society could maintain a coherent objective across 30 or 50 generations, with each new generation choosing to continue a journey they never agreed to begin, toward a destination none of them will live to remember choosing, requires a level of social engineering that has no historical precedent anywhere on Earth. Suspended animation offers a theoretical alternative. If crew members could be placed into a state of metabolic suspension, their biological clocks effectively paused, they could in principle survive journeys lasting centuries without aging. Science fiction routinely depicts this as cryogenic freezing. In reality, no technology capable of reversibly freezing and reviving a complex multicellular organism exists. The obstacles are formidable at a fundamental biological level. Water expands when it freezes, rupturing cell membranes. Ice crystals shred delicate tissue structures. Whole-body suspended animation for humans remains firmly in the realm of speculation, with no clear scientific pathway from where we are today to a working technology. It is not simply an engineering challenge. It is a problem that requires solving biology at a level we have not yet approached. But even setting aside the question of keeping the crew alive, there is the question of keeping the spacecraft alive. And this is where the interstellar environment reveals itself as an active adversary. The space between stars is not truly empty. It contains the interstellar medium, a thin haze of hydrogen atoms, helium, trace heavier elements, and microscopic dust grains. The average density is roughly 1 atom per cubic centimeter. A vacuum far more extreme than anything achievable in a laboratory on Earth. But at the velocities required for interstellar travel, even this whisper of matter becomes dangerous. A spacecraft traveling at 10% of the speed of light moves at 30,000 kilometers per second. At that velocity, every hydrogen atom in the interstellar medium strikes the spacecraft's forward surface with the kinetic energy of a high-energy particle. The cumulative effect over years and decades of transit is equivalent to standing inside a particle accelerator. A continuous bombardment of radiation that degrades electronic components, erodes structural materials, and slowly destroys any unshielded surface. Dust grains present an even more dramatic hazard. The interstellar medium contains microscopic solid particles. A dust grain massing 1 nanogram, a billionth of a gram, striking a spacecraft at 10% of the speed of light carries kinetic energy comparable to the muzzle energy of a small handgun round. A single invisible speck of interstellar dust would punch through the hull of any conventional spacecraft like a bullet through paper. At 20% of the speed of light, the energy quadruples. Each dust grain impact becomes equivalent to a rifle round. Over a journey lasting decades, a spacecraft would encounter millions of such particles. Without shielding far more massive than anything currently achievable, the cumulative damage would be catastrophic. And every kilogram of shielding added to the spacecraft increases total mass, which increases the fuel requirement, which compounds the rocket equation penalty. Cosmic rays add another compounding layer of degradation. These are high-energy particles, primarily protons, accelerated to near light speed by supernova shock waves. They permeate the galaxy continuously. In interstellar space, there is no protection. Cosmic rays penetrate spacecraft hulls, ionize atoms in electronic circuits, corrupt data, and damage biological tissue over time. An interstellar mission lasting 40, 80, or 400 years would subject its crew or its electronic systems to radiation doses orders of magnitude higher than a Mars mission. Without shielding far beyond current capability, neither the crew nor the computers would arrive intact. And then there is the slow, relentless decay of the spacecraft itself. Every mechanical system degrades over time. Seals crack, lubricants evaporate, metal fatigues, electronic components drift out of specification. The International Space Station, the most complex structure ever built in space, requires continuous resupply and constant maintenance by its crew. It has been operational for roughly 25 years and already shows significant wear. An interstellar spacecraft would need to operate for decades or centuries with no resupply, no replacement parts, and no possibility of rescue. The longest operating spacecraft in history, the Voyager probes, have survived roughly 5 decades, and both are experiencing progressive instrument failures. Extending that operational lifespan to centuries under the additional stresses of relativistic dust bombardment, cosmic radiation, and complete isolation represents a challenge without precedent in the entire history of engineering. What emerges from all of this is not a single barrier, but a series of compounding constraints. The biological clock limits mission duration. Generation ships create unsolvable social and engineering problems. Suspended animation remains biologically speculative. The interstellar medium bombards the spacecraft with radiation and impacts. Cosmic rays degrade both crew and electronics. And the spacecraft itself degrades over time, with no possibility of repair. These are not independent problems. They interact. Long travel times are not just logistically difficult, they're actively destructive. The longer the journey, the more damage accumulates, the more likely a critical system fails, and the lower the probability that anything functional arrives at the destination. The interstellar environment does not wait patiently for you to solve your engineering problems. It works against you every single day of the journey. This is a journey with a 0% chance of success. The galaxy is at least 13 billion years old. It began forming within a few 100 million years of the Big Bang, gradually building the spiral arms that now stretch across 100,000 light-years of space. For most of that 13 billion year history, the galaxy has contained billions of stars, trillions of planets, and conditions broadly compatible with the chemistry of life. Earth itself is only 4.5 billion years old, meaning the galaxy was already more than 8 billion years into its existence before our planet even formed. If life can arise on suitable worlds with any reasonable probability, and if intelligence can eventually emerge, then the galaxy has had an almost incomprehensible amount of time to produce civilizations far older and far more advanced than our own. Not by thousands of years, not by millions, but by billions. The numbers support this picture in striking detail. Statistical analysis suggests there could be roughly 40 billion potentially habitable Earth-sized planets orbiting Sun-like stars in the Milky Way alone. Add the far more numerous red dwarf stars, and the number climbs considerably higher. Water is one of the most common molecules. Carbon chemistry is ubiquitous. The raw ingredients for biology are not rare or exotic. Life appeared on Earth within the first billion years of the planet's formation, almost as soon as the surface cooled enough to support liquid water. If our planet is any guide, biology does not wait long to establish itself once conditions allow. Applied across billions of suitable worlds and billions of years of cosmic time, the implication is staggering. The galaxy should be full of life, ancient life, life that has had far longer to develop than we have. This is the foundation of what physicists call the Fermi paradox. In 1950, over lunch at Los Alamos National Laboratory, physicist Enrico Fermi looked up at his colleagues and asked a question that has haunted science ever since: where is everybody? If the galaxy is this old, this vast, and this rich in potentially habitable worlds, why do we see no evidence of other intelligent civilizations? No signals, no probes, no megastructures, no visitors. Every radio telescope ever built has listened to the sky and heard nothing but natural phenomena. Every survey of our solar system has found no artifacts, no engineered objects, no signs that anyone has ever been here. The sky is silent. The solar system is empty. And the silence is not for lack of looking. We have been searching seriously for decades, and the answer has been consistently and completely nothing. Dozens of explanations have been proposed. Perhaps intelligent life is far rarer. Perhaps civilizations inevitably destroy themselves. Perhaps they deliberately choose silence, hiding in what some theorists call a dark forest, where announcing your presence invites destruction. Perhaps they exist in forms so alien we cannot recognize them. Or perhaps they have moved beyond physical existence entirely. Each of these explanations addresses the paradox from a different angle. Each one requires assumptions that we cannot verify. And none of them is grounded in anything as solid and testable as the laws of physics. There is one explanation that requires no speculation about alien psychology, no assumptions about the rarity of life, and no theories about civilizational self-destruction. It is an explanation built entirely from the physics we have spent this entire discussion examining. They cannot get here. Not because they do not exist, not because they do not want to, not because they lack the intelligence or the ambition or the technology. But because the speed of light, the absolute maximum velocity permitted by the universe, is too slow to make physical travel practical across the distances that separate most star systems. The energy costs are prohibitive. The travel times exceed any biological lifespan for all but the nearest destinations. The interstellar environment actively destroys spacecraft over the timescales required. And the galaxy is not 30 light-years across. It is 100,000. The physics does not care how advanced a civilization is. It applies to everyone equally. Everywhere. Always. Consider what this means in concrete terms. Suppose an intelligent civilization exists around a star roughly 30,000 light-years from Earth. They are technologically advanced far beyond us. They have mastered fusion propulsion and can accelerate a large spacecraft to 5% of the speed of light, a capability that dwarfs anything humanity has ever achieved. They aim their ship at Earth. At 5% of light speed, the journey takes 600,000 years. 600,000 years ago on Earth, Homo sapiens did not yet exist. Neanderthals were still hundreds of thousands of years in the future. The entire arc of human evolution from the emergence of our species in Africa to the construction of particle accelerators and space telescopes fits comfortably inside the travel time of this single hypothetical mission. If that civilization launched their ship 600,000 years ago, it would be arriving right about now. But what are the odds that any civilization maintains the institutional will, the technological infrastructure, and the physical resources to support a 600,000-year mission? Push the numbers further. A civilization on the far side of the galaxy, 90,000 light-years away, attempting to reach Earth at 5% of light speed, faces a journey of 1.8 million years. At 10% of light speed, 900,000 years. Even at the wildly optimistic speed of 50% of light speed, a velocity that would require energy expenditures beyond any plausible projection and that no known or theorized propulsion system could realistically achieve, the trip takes 180,000 years. The Milky Way is approximately 13 billion years old. It has had plenty of time for civilizations to arise, develop, and attempt expansion. But the speed of light ensures that crossing the galaxy is not a matter of centuries or even millennia. It is a matter of hundreds of thousands to millions of years. Each journey is a civilizational marathon with no guarantee that the runners will still exist or still be recognizable as a civilization when they reach the finish line. Some researchers point to a concept called von Neumann probes as a potential escape from this trap. The idea envisions self-replicating machines that could spread across the galaxy without any ongoing support from their home civilization. A probe arrives at a star system, uses local resources to build copies of itself, and launches those copies toward additional star systems. Each copy does the same. The process repeats exponentially, and within a few million years, the probes could theoretically visit every star in the galaxy. The mathematics are compelling. Even at modest speeds of 1 or 2% of light speed, self-replicating probes could, in principle, colonize the entire Milky Way in roughly 10 to 100 million years, less than 1% of the galaxy's age. If any civilization anywhere had launched such probes at any point in the last several billion years, they should have reached every star system by now, including ours. They have not. Or if they have, we see absolutely no evidence of their presence. But the Vaughan-Newman argument contains assumptions that collapse under scrutiny. It assumes that self-replicating machines can be built with sufficient reliability to function across millions of years without accumulating fatal errors. It assumes they can extract and process whatever resources they find in arbitrary star systems. It assumes no failure mode, mechanical, computational, or environmental, halts the replication chain before it spans the galaxy. Each of these assumptions is enormous. Cosmic rays would flip bits in computer memory over geological timescales. Micrometeorite impacts would damage structural components. The resources available in each star system would vary unpredictably. And self-replication at the required level of complexity implies a degree of artificial general intelligence that humanity has not achieved and cannot yet fully conceptualize. Biology, the only self-replicating system we know works, has been running for roughly 4 billion years on Earth, and it still accumulates errors, produces dead ends, and generates extinctions constantly. A machine replicating across millions of star systems over millions of years would face analogous and compounding degradation. Then there are the proposed shortcuts, the theoretical mechanisms that might allow a civilization to circumvent the speed of light entirely. Wormholes, described by certain solutions to Einstein's field equations, could in principle connect two distant points in spacetime without traversing the intervening space. Warp drives, like the Alcubierre concept proposed in 1994, describe a bubble of contracted spacetime that moves faster than light. These ideas capture the imagination because they suggest that the prison has a door, that the laws of physics contain a loophole clever enough to exploit. But every known solution describing a traversable wormhole requires exotic matter, a hypothetical substance with negative energy density that has never been observed or produced. The energy requirements for creating or stabilizing a wormhole large enough to pass a spacecraft through are estimated at levels comparable to the total mass energy of a planet or a star. The Alcubierre warp drive, in its original form, required negative energy densities comparable to the mass energy of the observable universe. Subsequent refinements have reduced that figure, but the requirements remain astronomical, and the concept has never been experimentally validated. As of 2026, these remain mathematical possibilities within the framework of general relativity, not technologies, not engineering proposals, and not evidence that the speed limit can be broken. What all of this points to, the travel times, the energy costs, the biological limits, the hostile interstellar environment, the failure of every proposed shortcut, is a picture that is both deeply unsettling and strangely clarifying. The galaxy may be full of intelligent life. Billions of worlds, billions of civilizations, each one gazing at the same sky we gaze upon, detecting the same exoplanets, running the same calculations, and reaching the same devastating conclusion. The distances are too great, the speeds are too slow, the energy costs are too high, and the universe, as far as anyone has ever been able to determine, does not offer a shortcut. Each civilization is an island, surrounded by an ocean of spacetime that light itself needs thousands of years to cross. They can see the other islands in the distance. They can detect the faint glow of other fires. But they cannot build a vessel fast enough to reach them. Not within any timeframe that a mission, a lifespan, or a civilization's continuity could survive. The silence of the sky is not evidence of absence. It is evidence of distance. And in that distance, written in the mathematics of relativity and the geometry of a 100,000 light-year galaxy, may be the answer to the oldest question we have ever asked. We are not alone. But we may be alone in every way that matters. Forever separated from every other mind in the universe by a prison whose walls are made not of stone or steel, but of space itself, and the merciless, unbreakable speed of light. The total number of intelligent alien civilizations we will ever physically meet, 0.